4 phi is put in an energy to G, then which is legitimate, then instead of 1. So people at the beginning of general relativity have argued Newton's theory is much more simple. It has 1 potential. Here we have 10, so it cannot be true. You know, I mean, it's for aesthetical reasons. I mean, you don't want to make the world more complicated as it is. And it's a fair argument, but you can overdo it. It's the same later when this connection was generalized, people said, we have enough potentials in Einstein's theory, don't introduce new potential. It makes life complicated, maybe, but perhaps nature is complicated. This we have to take care of. And they are called Christoffel symbols. That can be also interpreted as so-called connections, Christoffel symbols, 40, as connections, and then usually they are attributed to Levi-Civita connection. It's also called Riemannian connection, so you have the choice. If you are in exterior calculus, you really talk about connections. Connection just means this is a quantity which connects one point to a neighboring point. That is what a connection is all about. A connection provides a parallel transfer from one point of a vector, for instance, from one point to the next point. And that is what Levi-Civita discovered. If you have a Riemannian space and all these complicated Christoffel symbols, then what these Christoffel symbols do for you is just that they parallelly transfer one vector from one point to the neighboring point, which is trivial in Minkowski space, but in a curved space it's highly non-trivial. So this was a big discovery. So, and in mathematics then one has a whole theory of connections, and this theory we will come back in the next hour, hopefully. Okay, now, so we have by a shear coordinate transformation we have produced a homogeneous gravitational field. This is this. And this is not a tensor, as one can easily prove, because in Cartesian coordinates is 0, in these coordinates is non-zero. The tensor which is 0 in one coordinate system is 0 in all other coordinate systems. So connection is not a tensor, it is a connection. It's a quantity of its own kind. And so do we have a tensor which is related to the gravitational field? Well, we just have to differentiate. I make it symbolically. You get the Riemann tensor, R little, proportional to the curl of gamma. If gamma were sort of a potential, like in electrodynamics, you have A, the curl of A is F. This is the analogy which one can use. So we have, and if you define it properly, it's R-I-J-K-L. And you can derive it just by, you take a vector, you carry it around a small loophole, and you look a small loop, and you look how the vector changes. It rotates a little bit. And this rotation is described by this curvature tensor. It's linked to a small area element, the loop, and to the vector. And for that you need a rotation matrix. So you can see the area element has two indices, antisymmetric, these are the first two. And the rotation is a matrix. You have rotation of a vector from one direction to another in two indices. So this is curvature tensor. I take here the conventions of Schout and Ritchie calculus, which not all people like, but this is the most useful book in this connection for gauge theories. So this is partial I, gamma, J, K, L, plus gamma, little, times gamma, little, I, antisymmetric, J, antisymmetric. Here we have a M, and then we have here a K, and here a L. This is the Riemann tensor in all its beauty. In Minkowski space-time, the Riemann tensor vanishes because we are only going in other coordinates. So the gammas fulfill in Minkowski space integrability conditions, namely that the curvature tensor is equal to 0. This is no, this is not a requirement. This is automatically fulfilled. It's in Minkowski space-time. So Minkowski space-time, this is equal to 0. And the whole trick of Einstein was now, of course, we know now that the curvature tensor depends on second derivatives of the metric, right? Because it's a connection is differentiated once, and the connection itself is the first derivative of the metric. The Einstein tensor depends on second derivatives. The Christoffel connection depends on first derivatives of the metric. Okay. And even in curvilinear coordinates, such things may arise. But only if a real gravitational field is present if R square, if R triple is unequal to 0. So now Einstein switched on gravity for us. In that he claimed that now gravity, since we know, according to our calculations, that in an accelerated frame we find the Christoffel simples. By the equivalence principle we know that the Christoffel simples must be able to describe a homogeneous gravitational field. Homogeneous gravitational field, first derivatives of the metric. Now, in a Minkowski space, it is homogeneous and R little vanishes. But if it's no longer homogeneous, then we have to relax this condition, and we have to set the Riemann tensor free, and we have, and this is then called the tidal gravitational field. Because if you look at it operationally, you see if you have two point particles moving nearby in a gravitational field, then the curvature tensor describes the attraction between these two neighboring point particles. In mathematics, this is called the geodesic deviation equation. So, for that, this is like the tides, right, on the Earth, the tides, flood and what is the other? What is flood, and if the water is high, it's a flood, and if it's low, it's, what is it called? Well, you should know it, you live on an island. You know, Newton was the first who made a theory of tides incidentally. High tide and low tide. Sorry? High tide and low tide. High tide and low tide. Okay. High tide and low, okay. Now we are. Here we are. And this tidal, so the tidal gravitational field is described by the Riemann tensor. And this is a tensor, whereas this strange Christoffel is not a tensor and has no invariant meaning, no physical meaning in a way, which is invariant under coordinate transformations. So this is the quantity which we were looking for. And this entered the scene just as the time is over, more or less. No, is it a quarter of an hour? How long is my lecture?
You have 10 minutes.
Okay.
Yeah, no, if you want to finish, okay.
No, I mean 10 minutes would be fine, you know, but I don't want to bore people too long. I mean, but who has no time can leave. I mean, okay, 10 minutes, okay? Because we just want to follow up, and this is now really my last part one section. No, this is not true. I just make 10 minutes and that's it. We have now entered, okay, let me see that I don't forget relevant things. The other thing is that one consequence which Einstein drew from this consideration is that light must be deflected by the gravitational field. And this is very simple, light deflection. you just write down the equation of a light ray is ds square is equal to 0. A light ray you can get by, you take Maxwell's vector equations and make a geometrical optics approximation, then you can extract light rays. And the light ray will follow geodesic, which is determined by this ds square equals to 0. Now in curvilinear coordinates, it's no longer a straight line. So in curvilinear coordinate and according to the equivalence principle in the gravitational field, light is deflected and the velocity of light changes. I always considered it for these bureaus of national bureaus of standards as a risky thing, also in the SI system, that one uses c square for defining time, etc. Even if we know that c is not a constant. I mean, at least in a gravitational field, c is not a constant. Only if you go to a freely falling system in a gravitational field, then in this freely falling system, c is a constant, but not in general. Of course, the effects are very small, so for many practical purposes it doesn't matter. But still, I consider it as a risky thing to take this as a sort of an assumption underlying our SI system of units.
Well, it's a matter of definition. So I think in the definition, they have to be a local inertial frame. However, on Earth, you see t is very small, so compared to 1 light year. So the effect on the clock is below 10 to the minus 18 fraction. So therefore, up to now, the clock is okay, unless you have a big clock system. And then, even if you move the precision clock by 1 centimeter, it can be detected now. You moved it by elevated by 1 centimeter. So and also just a little bit comment. So it's true that in curvilinear coordinate, light is not constant. So that means in non-inertial frame, light is not constant. So this is actually taken by Einstein in his 1911 paper. It's a variation of velocity of light. So to take a face value, so in 1905 he assumed constant of light, and in 1911 he said the variation of velocity of light in gravitational field. Okay.
Who cares about what I said yesterday? Yeah, that's very important, and I mean, as you know very well, in 1911 is published in his notebook. He made this calculation, and then the deflection of light came out with the wrong factor. And this factor was only improved after GR was discovered, where you had to include the spatial curvature in order to get the correct value of the deflection of light. So he had to correct this result later on. So I mean, this is a nice exercise for students to determine the deviation of the light in a Schwarzschild solution. Then you already see that it has a contribution from the G00 component, but also from the G11, G22, and G33. Okay, I think I should first I should here. This is was misnumbered. It should be 17. Just discovered that. And I have 18. And the last is general relativity and remaining space. General relativity and remaining space. So we have relaxed, we have this tensor, and we we look for the properties of this tensor, and we find corresponding deviations of the light and what we just discussed. Now, what is the coupling, and this is very important, the coupling of energy momentum to gravity can be now easily discovered. This is also left out in many textbooks. This is an argument which is due to Weil. If you take a dust particle, so which has an energy momentum tensor, which I call Tij, is equal rho is the density times velocity ui, uj, for velocity of the dust. Ui is for velocity. And you assume that to be a function of, a slowly varying function of x, and you multiply it by the geodesic equation in curvilinear coordinates. What you then get is the following. You get rho times d 2xi over ds squared plus t jk times gamma jk I equals to 0. That's a very important equation. So you see, if you multiply by rho, you get just here the rho, and here rho times these two, these are four velocities, give us the energy momentum tensor of this scalar dust. And this couples to this field. So you see, and this is analogous to, for instance, electromagnetic field. You have here F, say, Ki, and here you have the electric, this is the energy momentum current, you have the electric current, which is Jk. So this is really the Lorentz force density in electromagnetics. Field strength times electric current. So we have a test current, and this is really the definition of the field strength in electrodynamics, and that's the Lorentz force density. Lorentz force density. And you see that the current couples to this field strength. And in gravity, the Christoffel couples to the energy momentum tensor. So you see already that the energy momentum tensor plays a role like the electric current in electromagnetism. And this is a strong hint that energy momentum tensor should be the source of gravity in the same way as the electric current is the source of the Maxwell field in electromagnetism. However, the gravitational field is symmetric, the electromagnetic field is anti-symmetric, and these two indices, if you lower one index, it's just anti-symmetric. But this argument is a beautiful argument which shows that certainly this is a derivative of the metric, so energy momentum tensor is intrinsically related to the metric of space-time, and this is an important property which will lead us the way to the field equations of gravity, where this energy momentum tensor is really the source. As in the inhomogeneous Maxwell equation, the electric current is a source. Okay, this is 11 minutes more. Thank you for your patience.
Are there further questions for Professor Hehl?
One question is that in that equation, the crystal symbol is not a tensor. Will this affect anything here?
Well, so you are.
I mean, it's not a tensor. I mean, that's all I just say that there is a certain analogy. But I mean, this F is certainly a tensor. This gamma is not a tensor. This is true. But the there is a coupling of, I mean, this is the same as with the gravitational energy and so on. I mean, this is related to this question. But it's not a tensor, but it describes a homogeneous gravitational field as we learned. And this is coupled to this energy momentum tensor. I mean, there's nothing, I mean, what was the remark? I mean, it's correct, this is not a tensor, this is a tensor. And insofar, this analogy is sort of not too strong from this point of view. But from the point of view of the physical interpretation, I think it's, you can, well, I mean, even it must be like this, because in gravity you must be able to transform away this Lorentz force. In electromagnetism you must not, because it's tensorial. Gravitation, this force only appears if you go in the wrong coordinate system. If you go in the, well, locally in a Cartesian coordinate, Riemannian normal coordinates, then this stuff vanishes. Right? It's only true if you're not in a Riemannian normal coordinate system.
So may I make a comment? So in the genesis of, or in the change to a new thing or new paradigm, or in the step up of the recognition level, there are always fluctuations and dissipations. So here, it's a kind of a fluctuation. You need to have fluctuation in order to get you far enough to include the correct path. So here, if after general relativity, if you really want to be more rigorous, you can just take difference of this equation with a nearby path particle, and then it becomes geodesic deviation equation, and that is meaningful. But of course, this is a fluctuation which will lead you to something far enough if you read some definition of the meaning of gamma. Okay, so actually in the history, in the Newton's Poisson equation, you have the gravity side and you have the matter side. And the gravity side, people struggle to basically in 1911 to 1913 about the gravity side, and people try to use scalar field. And so the velocity of light, variation of velocity of light is due to a scalar field, and that was the first invention of Einstein to move it a little bit further.
To a tensor field.
No, there was no tensor field at that time. Then people try to find the right matter, whether it's rho or something, and then people found that rho, scalar field is invariant, is a tensor, I mean trivial tensor, but rho is not a tensor. People found out that, and then people try to correct it. So there are the electromagnetic force and for energy momenta by Minkowski, but at that time people were mainly looking for matter, not the radiation. So in 1912, Laue get a stress and tensor for matters. I mean, it takes some time. It's not just the gravitation part, and also the matter part. And then people realize the stress and tensor for matter. It's largely due to Laue. So then for the scalar field, Nordstrom find a few equations which was later. Nordstrom used the trace of stress and tensor. So that's one improvement, because trace of stress and tensor is invariant. Okay, so the equation looks invariant, and so shortly after Nordstrom, Einstein and Fokker and Einstein, I do not remember, but anyway, two of them make the Nordstrom equation R equal to T, R proportional to T. So that is full invariant. So Einstein then thinks...
This is a scalar.
a scalar, so
The curvature scalar.
curvature scalar is proportional to t. But this, although it's full invariant, it doesn't give light deflection. But of course, there was no test of light deflection at that time. So that is 1913. Einstein collaborated with Marcel Grossman on the true generativity, the tensor. So, but Einstein still think whether one has to be the tensor, I mean the final theory to be the theory proposed by Einstein and Grossman, or this theory. And finally, he gave up the tensor one in 1913, which is awfully close to generativity at the end, because it's not covariant or something. He made a mistake. I do not know. I have to find out who